Language models are really good at understanding and generating text, but they don't naturally understand physical signals like current or vibration or pressure. A foundation model for physical signals like Newton does. So in this paper, we're exploring how we can efficiently build a bridge between physical signal models and LLMs. We train a very small mapping network to convert Newton's sensor embeddings into token-like vectors that the language model can understand. This creates a bridge from the physical signals into a language domain with only a few million parameters that need to be trained. The result is that the model can generate very rich, contextually dependent interpretations of what the sensor is observing in the real world through natural language. For example, here we can see that Newton, out of the box, is able to cluster together different INU signals according to the underlying human activities, despite never having been trained on semantic human labels. Training is this fast because we're keeping both of the key model components frozen, the physical world encoder as well as the language model. In the paper, we built a proof of concept of this model alignment technique using data from INU sensors on vehicles. We showed that a very efficient mapping technique could be implemented, bridging between the Newton physical world encoder and a pre-trained LLM that identifies whether roads, according to their condition, are bumpy, smooth, asphalt, cobblestone, or other different types of physical conditions. The Newton physical world encoder naturally clusters together different underlying physical behaviors, as seen through the structure of the physical signals. So we see rough roads clustered with other rough roads, and smooth roads clustered with other smooth roads. Because of this natural structure inherent in the Newton physical model, we just need to convert this structure into a form that the language model can understand. And we can do this with a few million trainable parameters rather than having to train everything from scratch. This means that we have a very compute and data efficient method of aligning a physical world model with a language model so that we can generalize at scale to different types of sensors and different contexts. When we have these efficient mapping techniques from the machine native understanding of the physical world model and our own human interpretation of the world, we see this potential for physical AI to reveal new discoveries and understandings of how the real world behaves beyond what we currently understand today.